Muy buenos días a todos. Un gusto estar nuevamente presentando la charla técnica en esta nueva jornada. Como comentamos al iniciar este ciclo de charlas, la GIZ ha estado del 2015 promoviendo el uso del hidrógeno, considerando el gran potencial que tiene Chile para generar este hidrógeno en forma verde, en forma sustentable, a partir de recursos renovables. Y hoy, en el marco del proyecto de descarbonización, además, aparte de la parte técnica, nosotros estamos atendiendo distintas temáticas respecto al uso del hidrógeno, como el tema de normativa del hidrógeno, identificación de impactos ambientales que estos proyectos podrían tener a futuro, potenciales generación de futuros empleos de este nuevo mercado, la estrategia del hidrógeno, estamos apoyando también organizando junto al Ministerio de Energía y Corfo el evento internacional del Summit 2020, que será en noviembre, el 3 y el 4, y financiamiento climático verde que servirá para proyectos de hidrógeno y otras tecnologías innovadoras, entre otras cosas. Entonces, en este camino estamos, ya lo mencioné, hemos visto la necesidad de profundizar o ir más a fondo en las distintas aplicaciones del hidrógeno y en distintos aspectos. Por lo cual, nosotros hemos gestionado todo este tiempo conversaciones con empresas internacionales de gran experiencia para que nos entreguen ese conocimiento y así ayudar de alguna forma a acelerar el desarrollo del hidrógeno en Chile. Quería mencionar, como siempre, a nuestra contraparte del Ministerio de Energía que apoya estas charlas, así como a los colegas de HO Chile, la Universidad Técnico Federico Santa María, el Centro de Energía UC, el Comité Solar de Corfo y la revista Electricidad. Muchas gracias a ellos. En esta oportunidad vamos a conversar sobre el almacenamiento y compresión del hidrógeno, proceso clave en toda la cadena de valor del hidrógeno. Mira, sabemos que el hidrógeno tiene 3 veces más energía que la gasolina cuando estamos hablando en términos de masa. Pero cuando hablamos en términos volumétricos, en términos de volumen, en condiciones normales el hidrógeno se queda bastante atrás, y es por esto que para aumentar esa densidad se requiere la compresión. Ya, como dato, la densidad del hidrógeno a un bar de presión, condiciones normales, es de 0,08 kilos por metro cúbico. Metro cúbico, sí. Pero cuando vamos a presiones, como por ejemplo las que se usan en los buses de celda de combustible, a 350 bares la densidad aumenta a 23 kilos por metro cúbico, es decir, se multiplica por 287 veces la densidad, y por eso el tema de la compresión en el caso del hidrógeno es súper importante. Para explicar esto y más, hemos gestionado una charla con la importante empresa norteamericana Plug Power, con amplia experiencia en sistemas estacionarios de almacenamiento, producción de energía, transporte y movimiento de material, específicamente también montacarga, y con clientes tan grandes como Walmart, Amazon y otros, BMW entre otros también, con una alta participación en el mercado norteamericano de suministro, especialmente también en esta pandemia que nos está afectando, ha crecido ese movimiento. El presentador de esta charla será Fernando Corral, que es VP Sales and Channel de Latinoamérica, ha trabajado en la industria del movimiento de materiales durante más de 39 años, con Raymond Clark & Komatsu, lleva 10 años con Plug Power, y a partir del 2014 él y su equipo se centraron en ampliar la presencia de Plug Power en los mercados minoristas y de distribución. Actualmente es responsable de expandir el programa Channel Partner en Plug Power, al mismo tiempo de expandir la presencia de esta compañía en el mercado latinoamericano, en LATAM. Entonces, como en versiones anteriores, la presentación va a ser en inglés. Las preguntas, por favor, háganlas en el chat. En español, no hay ningún problema. Nosotros las vamos a compilar y las vamos a traducir para que al final de la presentación Fernando pueda aclarar esas dudas. Así que sin más, Fernando, la pantalla es toda tuya. Te escuchamos y después volvemos con las preguntas. Gracias.
Bueno, muchas gracias, Rodrigo. ¿Me escuchan? Sí.
Perfecto, se escucha.
Well, good morning, good evening, good afternoon, wherever you find yourselves in this world economy. Just a little bit about Plug Power. Plug Power in 2008 focused on material handling equipment and essentially created a market where no market existed. In 2008, there was only 30 fuel cells powering forklift trucks. And the early adopter was Walmart. As you can see, we have vast experience. Currently, there's over 38,000 forklift trucks in the world, primarily in North America, that are running on fuel cell technology. One of the most important aspects of the amount of product that we have out there is the fact that we collect data every time a hydrogen fuel cell is refilled. We use that data, as you can see, through over 300 million operating hours. We use that data not only to make our equipment more reliable, but more importantly, more fuel efficient. Quickly, our corporate office is in Latham, New York, upstate New York, near Albany. We have service support centers in Ohio and in Illinois. We are the largest MEA manufacturer in the world. We've surpassed that mark back in February. We also have our stationary product is being built in Spokane, Washington, and we also have operations in France, which serve our European operations. Plus, we recently purchased a company in Montreal, which is specializes in miniature fuel cell technology for drone and robotics. As you can see, and as Rodrigo mentioned, Walmart was an early adopter. Amazon began adopting the technology 4 years ago. And currently, between Walmart and Amazon, they operate close to 80 facilities in North America running on fuel cell technology. And the majority, if not all, of these companies make the business case for fuel cells work. The fuel cells also support their sustainability objectives, but if you can't make it work on the bottom line, it's very difficult to adopt the technology. And these companies, amongst others, have done so. Our hydrogen strategy is quite simply to be vertically integrated. We have been consumers of hydrogen for since 2008. In 2020, we purchased an electrolyzer company, and we also purchased a hydrogen company in the U.S. So now Plug Power produces and consumes currently close to 30 tons of hydrogen per day. And our objective by 2024 is to have to consume 85 tons per day. And the important objective is green hydrogen will account for almost 50% of that consumption. This is our fuel full suite of products. We have stationary products or progens, and these are used in our stationary products. They're also used in our on-road vehicles, everything from light-duty trucks to eventually Class 8 tractor trailers. We started our fuel cell technology, deploying the fuel cell technology in material handling, and that continues to be the bulk of the units produced and the revenue generated for Plug Power. In 2013, we developed and started implementing and installing our own hydrogen storage, compression, and dispensing systems. And then we maintain our product on our customers' behalf. These are Plug Power trained and supported technicians, and we monitor all sites 24/7 to make sure that our customers have uninterrupted fuel supply. Again, material handling has been the backbone of our production and our expansion, but Plug Power has, as we'll see later, also embraced the on-road markets, the GSE markets, robotics, drones, etc. Quickly, Rodrigo mentioned a little bit about hydrogen in the introduction, but just quickly we can go through what is hydrogen for those that are not familiar with it. Well, it's the lightest, smallest element in the universe. It's odorless, colorless, tasteless. It's really non-toxic. It disperses at 20 meters per second. So in distribution centers where the ceilings are high, between 10 and 15 meters high, there is no ventilation required for indoor dispensings, as you can see in the picture to the right. It has a very low radiant heat, and as Rodrigo mentioned, it's 3 times the energy content of gasoline. This is just basically for information purposes, but as you can see, even though hydrogen is probably the most regulated fuel on the market, it's probably one of their safest, and that's because it is very highly regulated, but also because of its properties. The auto ignition temperature is the highest of the fuels shown. Pure hydrogen flame does not produce any smoke. It has no radiant heat, so it does burn at a high temperature, but you can put your hands around a flame and not too close, but you can put your hands around a flame without feeling the heat. Whereas gasoline and carbon fuels release carbon, and the radiant heat is substantially, and that's what generates the expansion of any flame. These next 3 slides, I won't go through them in detail, but just to say, that again, hydrogen and the hydrogen components or equipment that is used to supply energy to on-road vehicles, material handling equipment, are very regulated, and Plug Power follows all the standards, especially NFPA 2, which was the National Fire Protection Association codes and standards that were developed specifically for the emerging hydrogen technologies. Again, these are the codes and the agencies that have approved the hydrogen fuel cells for operation, not only in the US, but also in Canada and in Europe. This is the list of certifications for our Gen Fuel systems. Again, approved by the local authorities and also national authorities in North America and internationally in Canada and in Europe. And now I want to focus on the main topic, which is compression and storage. but I also wanted to touch base on the hydrogen source. It's very important to understand where hydrogen comes from, at least at the industrial commercial level. It's important to understand how it can be transported. And then obviously, like Rodrigo mentioned, the compression and storage is a key component of being able to maximize the energy delivered by hydrogen. And then hydrogen dispensing obviously is a key component of the cycle. For those that may not know, essentially hydrogen is produced at the commercial and industrial level three ways. It's by an electrolysis, meaning you separate the H2O into hydrogen and oxygen. The hydrogen is then captured, and it's probably the purest hydrogen produced. In North America, electrolysis is not at the forefront of production, but by 2024, like we mentioned, we see almost at least the hydrogen that Plug Power is going to consume is going to be green hydrogen through electrolysis using renewable energy as the source to produce the hydrogen. There are several plants in North America and in Europe that also capture hydrogen that is produced as a byproduct of a chemical in chemical factories. So that hydrogen technically does not have a carbon footprint, but the vast majority of hydrogen produced in North America and a good portion of the hydrogen produced in throughout the world is reformation. So you take a carbon natural gas for the most part, and you strip out the hydrogen. And the problem with that, if you don't capture the carbon dioxide, that is released into the atmosphere. As we mentioned, delivery options are a key component of supporting the hydrogen economy. If you can produce it, but you can't deliver it economically, it becomes very difficult. So in the majority of the hydrogen in the United States, in North America, is liquid hydrogen. And one of the reasons why there is such a high capacity for liquid hydrogen is because of the NASA shuttle programs that required liquid hydrogen. But now that has been pulled back, the space programs have been pulled back, Plug Power has become the largest consumer and purchaser of liquid hydrogen in North America. Like I said, we consume close to 30 tons of hydrogen per day. You can see there's also low pressure gaseous hydrogen, either in tube trailers, and also on the far right, you can see what the system, a low pressure, low usage system looks like. You have a tube trailer, you have compression, you have two high pressure storage systems, and then you have a dispenser. And then next to liquid hydrogen, the most economical way of transporting hydrogen is at high pressure. And Plug Power has invested very heavily in these assets. Everything from a high pressure trailer that is towed by a pickup truck that contains up to 200 kilograms of hydrogen at 350 bar, all the way up to a tractor trailer using a cascading system that has a capacity of 900 kilograms of high pressure hydrogen. This is basically the standard liquid system in the U.S. You have the liquid tank, which is refilled by a tractor trailer that brings liquid hydrogen. You have the high pressure storage tanks, the vaporizer, you have the skid, the vent stacks, and the compressor. And essentially here, what we do is we take the liquid hydrogen, we run it through compressors or pumps, liquid pumps, and we compress the hydrogen up to 400 bar, and then liquid hydrogen is released into the vaporizer and then into the storage tanks. And that's the majority of the systems that we have in operation in the U.S. are these liquid systems, because liquid is the most economical way of transporting hydrogen, because you can transport such high volumes in liquid form. Like I said, we take the liquid pumps. This is the compression systems that we use to compress it to 400 bar. It's liquid pumps, and you can see the picture on the right, the liquid tank, and is that liquid hydrogen is released into the pumps, compressed, and then released into the manifolds. And these manifolds basically control the hydrogen that is at pressure, and basically released from there. It's released into the high pressure vaporizer. So liquid hydrogen converts into a gas within 7 to 10 degrees difference. So once the hydrogen at compression at 400 bar is released into the vaporizer that you can see in the top left, just the exposure to the ambient temperature turns it into the gas. And then from the vaporizer, the gas is stored at pressure in these high pressure tubes. And each tube will contain 20 kilograms of hydrogen. And from these tubes, then we run lines into the distribution center or to an outdoor dispenser, and basically connect it to the dispensers where it's dispensed to the equipment. These tubes are split into high bank and low bank, and that's important because we want to make sure that we always maintain pressure at the dispensers, because if we lose pressure at the dispensers, the refueling time is extended, and that impacts the business case. We also, as we mentioned, electrolyzers in Europe are becoming more and more popular in the production of hydrogen. In the US, we expect that that is going to also be the case. And that is one of the reasons why Plug Power invested in the in Giner ELX, which is now Plug Power electrolyzers. But essentially the same system when it comes to compression and storage. You have the hydrogen, which is produced in the container. It's all self-contained electrolyzer. The hydrogen is then released into the compression systems that you can see in the top left-hand corner picture. And then from there it goes through the manifolds, which control the flow of the high pressure hydrogen, again at 400 bar, into the high pressure tubes. and again, each tube is about 20 kilograms of high pressure of hydrogen at high pressure. This is the standard PDC compressor. It's a two-stage diaphragm compressor. And we use, in liquid systems, we use this compressor to manage the boil off from the LH2 tank, the liquid tank. And it's capable of compressing up to 95 kilograms a day. In other, when we do not use liquid pumps, we will have 2 of these compressors, or up to 3, depending on how much hydrogen is being consumed on a daily basis. Now I'd like to talk about a couple of very interesting projects that we had worked with a partner in Chile. The first one is, I think it's a lot of you may be familiar with, because it is a big deal in the mining industry. But it was basically to convert the truck, the Komatsu truck, into consuming hydrogen, and the numbers are staggering as far as dispensing. Because the requirements were 200 kilograms per fill, 4 fills per day, and we needed to be somewhere 10 to 15 minutes per fill, which was a substantial objective. It was all at 350 bar. We did not supply the electrolyzer. We, Plug Power, focused on supplying the compression, storage, and dispensing. So this project was kicked off in June of 2020, and it's currently being expanded, and it's working very well at this stage. So as you can see, it's this is where Plug Power focused on. We received the hydrogen from the electrolyzers at 30 bar. We compressed it to 350 bar, and or 450 bar. Apologize. And we stored it in the tanks. And then, as needed, we had 4 dispensers that would allow us to fill the truck in the required 15 minutes. This is the storage that we developed. Again, containerized, easy to transport, easy to install, and in this case here, the requirement was 1 ton. But we have 1.2 tons of hydrogen capacity in these in this 45-foot containerized compression skid. Storage skid. This gives you an idea as to the compression, the compressors that we use, the PDC compressors. Again, it allows us to supply the need of this high throughput application. It was a challenge when the compression systems together, again containerized, and this was all very important. We like to build and run all our systems before they are shipped. So when they arrive on site, they're easy to install and connect, and we can be up and running in days as opposed to be up and running in weeks. In this case here, the previous example was delivery, dispensing of hydrogen. So the compression, storage, and dispensing. In this case here, it's the same production of hydrogen using an electrolyzer. So our system, our skid, compressors receive the hydrogen at 30 bar. We compress it to 200 bar and we store it. And in this case here, this hydrogen was then used, would be used to, as needed when power was not available. So the electrolyzer would produce hydrogen using solar power during the day. We basically store the hydrogen during the day, and then that hydrogen is used to power equipment or generate energy at night when there is no solar power available. Again, just a quick diagram to show it's the same compression systems that we use. We try to standardize on these compression skids because it makes it easier to deploy and maintain on site. Just quickly, for those that may not know how a fuel cell works, essentially it's we do not combust the hydrogen. We essentially borrow the energy from the hydrogen molecule, and our systems are proton exchange membrane systems. And as you can see, the key component of the fuel cell or the stack is the proton exchange membrane, and that's the MEA. And essentially, it just allows the hydrogen the hydrogen or the electron is not allowed to go through the proton exchange membrane. So the membrane allows the proton to go through. The electron is separated, and when it's separated, isolated, we capture the energy of the electron, and then the electron and proton recombine. We bring hydrogen, oxygen from the outside, from the air, and the only emissions produced are heat and water vapor. So essentially, a fuel cell that produces energy is the reverse of an electrolyzer that produces hydrogen. An electrolyzer splits the hydrogen and oxygen. A fuel cell then recombines the hydrogen and oxygen to produce deionized water. A fuel cell system is just a series of components that work to store the hydrogen in a high pressure tank. Then that hydrogen is released into the stack. And as we saw previously, the energy from the hydrogen molecule is then captured, and that that energy is then delivered to a lithium-ion battery, and then that lithium-ion battery is primarily the source of energy for whatever vehicle is working is demanding power from the fuel cell, and that's we call that the peak energy device storage, because especially in material handling or even in on-road vehicles, material handling, when a forklift truck lifts a 3,000-pound load to height, it could draw 200, 250 amps of power. Well, the fuel cell stack would not be able to deliver that power instantaneously, but the lithium-ion battery does. And as the truck as the forks are being dropped to the floor, the stack recharges the lithium-ion battery. So the battery is always fully charged and delivering constant voltage. This is just a quick highlight of the systems that we have. Safety components for the fuel cell. Each fuel cell has their own hydrogen detection system that will shut down the fuel cell if concentration of 25% LEL is detected. So we are very conservative in that regard. We also regulate and maintain pressure, and temperature is very important for the fuel cell because if we do not maintain the pressure or the temperature within a nominal range, the proton exchange membrane or the MEA will dry up then if it dries up and cracks are produced, then the separation of the proton and the electron does not happen. The electromechanical reaction does not occur. I just wanted to also take a little bit of time to show where plug power began, like we mentioned in material handling, and we started with pallet jacks, which produced 3 kilowatts of power, and forklifts that had fuel cells that produced 11 kilowatts of power. Well, up to now, we have developed fuel cells or engines that basically will produce 60 kilowatts of power. We have FedEx vehicles that are running in Albany. We have ground support equipment which use the 20 kilowatt stacks. We have, as you can see, the DHL and FedEx units which run with 30. And by the end of 2020, we'll have a 100 kilowatt stack that will allow us to run our systems in buses, Class 8 trailers, and yard dogs, which our customers are very interested in because these yard dogs are diesel consumers, and they are always working, and they're always confined to the distribution network. So the amount of pollutants that are released are substantial. We also have a substantial deployment of stationary sites, which provide backup power for cell towers and communication systems. By the end of this year, we will have produced our large-scale backup power systems that we plan to deploy beginning in 2021 to replace diesel gensets. These backup systems will be up to 15 megawatts using our 1.5 megawatt fuel cell technology. Again, one of the things that we are really focused on is the on-road vehicles, the fuel cell electric vehicles. And the reason why is because, like one of our customers put it to us, is he's a courier delivering packages, but he wants to electrify his fleet. Well, the only way that you could electrify a fleet and get the range that you need without having to take up valuable space within the vehicle with batteries is with hydrogen fuel cells. So the FedEx vehicles that you can see depicted, that was EV vehicle converted with a range extender system, and it extended the range from about 75 miles to close to 160 miles without impacting the payload that they were able to carry. And again, like I mentioned, we are focused on producing fuel cells for drones, the last mile delivery systems that Amazon, UPS, FedEx are looking at. Also robotics, as you can see in the bottom right, that's an Amazon facility. Amazon has asked us to power these systems with fuel cells, and then automated guided vehicles along with ground support equipment. So this is the future for Plug Power, and being vertically integrated, it allows us to control the fuel supply. It allows us to control the delivery, the compression, the storage, and dispensing, the critical aspects of the hydrogen economy. And that, Rodrigo, is the end of the presentation.
Okay, thank you very much, Fernando, for the presentation. You have to consider Fernando wake up very early because he's in California, and we appreciate your effort. As we saw in the presentation, the compression, storage, and security of this project, of the processes is key for the development of the project. And it's important for the companies to understand the technical aspect on the correct handling of hydrogen in function to developing the project and planning. Yeah, it's very important in this topic. And we have many questions, several questions here. And now we will start with the question and answer. And the first question is, let me see, okay. Yeah, it's a very specific question. It's, they ask about the slide 10 in the comparison of energy density by volume, and slide 10. Under what condition are the pressure and temperature considered for hydrogen and natural gas?
I could verify exactly what those temperatures would be, but my understanding is that it's ambient temperature.
Okay. Yeah. Here is a question about the regulation, especially related with the security. Yeah, we have a question about the installation of, or the facility of hydrogen. Are there restrictions or barriers to installing hydrogen refuel station in residential areas in the United States? What can you say about that, about the regulation, about the norms or security aspect, etc.? Can you explain that?
Yes, NFPA 2, as I mentioned, was designed and developed to address the hydrogen economy and the hydrogen equipment. And there are setback provisions in the hydrogen in NFPA 2 that dictate how close hydrogen can be to different types of equipment, spark generating equipment. So for instance, a liquid system, a liquid tank needs to be 75 feet away from any open doorway, any intake for ventilation systems, any equipment that may produce a spark, and so on. But gaseous hydrogen, because it disperses so quickly, it's only 20 feet away. So in regards to residential areas, these setbacks are very similar to the setbacks required for the gasoline or propane that is being stored and dispensed in by the gas stations. So in California specifically, there's probably 60 hydrogen fueling stations that basically also offer diesel, gasoline, propane. So all these fuels are in the same area, but the distances required from residential areas are not impacted because it's generally only 20 to 30 feet.
Yeah, and in talking about the charge, on the charge, in case you had to provide the hydrogen from outside or by trucks, etc., there is a special consideration in that. Yeah, because when you see the trucks in the conventional fuel station, is the truck, you can see the truck. But in case of hydrogen, it's different. You have to take other consideration in order to charge this station in this case.
Yes, in liquid hydrogen, it's you have to have setbacks when you're delivering the hydrogen, but in gaseous form, it's very similar to the setbacks when you're delivering gasoline and other fossil fuels.
Okay. Talking about the cost and efficiency, could you tell us about the cost and efficiency of hydrogen compression and storage? Some dates, some information about that?
About the cost, are you saying?
Yeah.
Well, the cost of it's difficult to pin down a cost associated per kilogram of hydrogen because again, there's different ways of compression and storage. And it also depends, as far as compression is concerned, both compression and storage, the cost associated with the molecule of hydrogen is dependent on the pressure that you're going to end up with. So we work at 350 to 400 bar. The automotive industry is going to 700 bar, and that is several times more expensive to compress the 700 bar and store at 700 bar than it is at 350 and 400 bar. So there, I will ask the question of our engineers and our hydrogen team, and I can supply that information, Rodrigo, to you at a later date, and you can maybe send it out to the participants.
Okay, thank you. Yeah, a question related with that, and for distribution, what's the most economical way? The question is liquid or gas compressed hydrogen? What is the benefit of the high pressure versus liquid, for example? Can you compare or describe in what situation you can use, or it's more suitable to use the liquid or gas, etc.?
Well, it's liquid is the most economical way of delivering hydrogen, because you can transport many times, 600 to 800 times volume compared to gaseous hydrogen. So liquid will always at this stage today is the cheapest way of moving hydrogen from the plant to the end user. Compressed hydrogen is the next economical way, and low pressure hydrogen is the most expensive, because you can only those low pressure tubes that or tractor trailers that can only carry about 200 kilograms of low pressure hydrogen versus 900 kilograms for the same tractor trailer at high pressure can transport 900 kilograms. And just to give you an idea, a trailer with liquid hydrogen will transport anywhere from 4,000 to 5,000 kilograms of hydrogen and in liquid form. That being said, though, because electrolyzers are coming down in cost and becoming more prevalent, on-site generation, especially if you're using renewable energy, is becoming more and more economical because you don't have to transport that hydrogen, and transporting hydrogen is probably the largest single cost component for the hydrogen molecule delivered to end users.
Okay, I will ask you some later if you have an article for describing this comparison between liquid and gas compressor, if you have.
Okay.
A question relate with the standard pressure. What are the standard storage pressure for the different hydrogen applications? You show different applications. Can you explain that?
Sure. For material handling, we're at 350. 350 bar is what we deliver hydrogen at the dispenser. We store it at 400 bar because we want to make sure that we always maintain 350 bar, which is 5,000 psi. But we store it at 400 bar. The automotive industry, because they need to extend the range of the hydrogen vehicles, are going to 700 bar. But the cost difference between 350 bar systems and 700 bar systems, it's substantially. It's not linear. It's many times, several times more expensive. The storage systems that you saw in the second example, when you're at 200 bar, those are for systems that you store energy. You're storing energy, but most systems that we work with and the expertise that we have is at 350 bar and 400 bar.
Okay. Question related with a small project. And is there available some small onboard production of hydrogen and fuel cell for a vessel? Assume energy is based on PV, for example. I think it's referred to small production in case small projects.
Yes, there is. I mean, our electrolyzer division is, as a matter of fact, we're working on a demonstration system that we hope to have available next year, which will fit into a 20-foot and 40-foot container. And that system will have an electrolyzer. It will have a compression. It will have high pressure storage, and then it will have also a dispenser. And those systems we expect will be able to produce up to 20 to 30 kilograms a day, and be easily transportable. So all an end user would need to do, and these we are developing for demonstration projects, for proof of performance, pilot programs, and all the objective would be to take this container, deliver it on site, connect power and water to it, and it would be a self-contained hydrogen production, compression, storage, and dispensing system. So there are systems, and I showed a representation of a small system that is being fed by a tube trailer. It uses a small compression system, a couple of high pressure storage tubes, and a dispenser. Well, those are available, and they can handle consumption levels of 20 to 30 kilograms a day easily.
Mm-hmm. And talking or going back to the transport, hydrogen transport we know is critical, and when one must to consider using hydrogen in another place than where the hydrogen is produced, what are the considerations to take into account, for example, for a company who was to develop a hydrogen project, when decide the production of hydrogen on site versus bringing it from another place in gas compressed or liquid hydrogen, when you must choose one option on another?
Generally speaking, it's the two main factors. One is the distance between where the hydrogen is produced and where it's going to be consumed, because that transporting hydrogen, like I mentioned, is the single the largest cost component. So the distance between production and consumption. And then the second one is how much are you going to consume on a daily basis? If you're only going to consume, let's say 20 to 30 kilograms a day, then using a low pressure tube trailer that is at 200 bar, transporting 200 kilograms to a site and then compressing and storing it at 350 bar, well, that may be feasible. But if you're consuming 100 to 150 kilograms a day and liquid hydrogen is not available, then on-site generation using electrolyzers and renewable energy is probably the most economical way of supporting that operation. So essentially, it's distance and also how much you're going to consume on a daily basis that determines whether you produce on site or you transport.
Okay. Talking about environment, in Chile we are developing or supporting the develop of the regulation, normative, security aspect, etc. But also we are talking about impact over the environment. And what are the impacts of environment of the different application of hydrogen or the use of production of hydrogen? What can you say about that?
Well, I mean, hydrogen is the cleanest energy. If you can produce the hydrogen using renewable energy. So, for instance, if an electrolyzer is used on site, if you do not have renewable energy and you rely on energy from the grid, that hydrogen has a carbon component dependent on the makeup of the grid. So how much energy, how much of the electricity from the grid is produced by using fossil fuels versus using hydropower or using solar power. So, but if you're using, if you have an electrolyzer that is attached to a solar array, and it's on site, so you don't have to transport that hydrogen. That fuel, that hydrogen fuel, is completely green. It's carbon neutral because you're using the sun to separate the oxygen from the hydrogen. You're using the sun to compress it, and you're using the sun to essentially dispense it and consume it. So being able to power electrolyzers with renewable energy, that would have the largest impact on sustainability in Chile.
Okay, and change the topic a little. In Chile, we have many big retail companies, and talking about the forklift, what do you think or what is the interest of the large company to use hydrogen forklift in their operations compared to other technologies such as only batteries or gas forklift, for example? Can you say what is the advantage, what are the different aspects you can decide for one technology and other?
Yes, of course. The bottom line is that in gas technologies, a lot of companies that are retail distributors, especially in the food industry, do not run internal combustion vehicles inside, and obviously it's because of the fumes that is being released. So the majority of our customers that are operating distribution centers like Walmart, like Amazon, they were using lead-acid battery technology, and those lead-acid batteries have a finite energy capacity. So an industrial lead-acid battery would be able to give you approximately 6 to 7 hours of energy before it has to be recharged. In operations like Walmart, like Amazon, they operate 24 hours a day, 7 days a week in the United States. In Chile, the requirement, the operating hours are 6 days a week, but they still operate 24 hours a day. So what happens is you have to take out a battery and then replace it with a fresh recharged battery so the operator can continue their work. So the time that the operator has to stop work when the battery has been discharged until the time that the operator is back working with a new recharged battery, in a lot of cases, it's about 15 to 20 minutes. So if you have to change 3 batteries a day, you're going to lose 45 minutes to an hour of production. You're paying that operator to essentially not work because they have to go change the battery. So in the average fleet of material handling equipment, you're in these large retailers, you have a fleet of anywhere from 200 to 275, 300 pieces of equipment. So you can see an hour lost a day times 300 pieces of equipment times 365 days, that is a substantial cost savings, because with fuel cells, you can run a fuel cell on one tank for approximately anywhere from 6 to 12 hours, depending on the operation, but it only takes about 2 to 3 minutes to recharge. Okay. So that is probably the largest benefit that these customers get from going to fuel cell technology. Obviously, there's others, because one of the other benefits is you do not need a battery room, and some of these battery rooms have a lot of consume a lot of energy. They have a lot of expensive equipment to change batteries, where with 4 dispensers, you can supply a fleet of 300 pieces of equipment, and that dispenser only it takes up about 20 square feet of space.
Okay, talking about the fuel cells, does your equipment require air and water purification system, and what are the approximate associated costs for that? And to complement, is it possible to let the fuel cell run empty and keep it in that way for a while?
Well, we don't require water or for our fuel cells. As a matter of fact, we generate water or water vapor. We do require air intake because, like I mentioned, we need to maintain the temperature of the stack so it continues to function properly. So we use a combination of a heat exchanger and airflow that we draw in from one side, and it keeps the fuel cell and the stack within that nominal range of temperature. So we do require air. It's very similar to how the automobile is cooled. It has a radiator or a heat exchanger with liquid, which is generally glycol water mix, and then airflow. So we use the same.
Yeah. Okay, no, I have to clarify, maybe there is a confusion in order to, an electrolyzer needs water.
Correct.
Fuel cell needs hydrogen, yeah, in order to understand better. And other things that is, in Chile, we are just developing the hydrogen regulation, aside from industrial gas. How is this process in the United States and in the case of Plug Power products, and what were the concerns of the companies regarding this new fuel?
Well, I think the major, the original concern was around safety. You know, hydrogen, like I've mentioned, is a highly regulated fuel, and even though that makes hydrogen systems more expensive than fossil fuel systems, it also makes the hydrogen fuel a lot safer. So the major concern at the beginning when we were deploying these systems was the safety systems that are associated with hydrogen. And but that is less and less of a concern because hydrogen is so prevalent, at least in the US and in Europe. So it's a very safe fuel, and the worst thing that you can do with hydrogen is to confine it. So that's why there's these dispensers and these outdoor systems are not enclosed, because if there is a venting of hydrogen, what you want it to do is just vent to the atmosphere. So I would say that safety was the biggest concern, but not so now. And NFPA 2 went a long way to satisfy the end users like Walmart and Amazon and Kroger, General Motors, BMW, but also more importantly, they're insurance companies. So now most major insurance companies we don't get involved with them anymore because they have adopted and accepted NFPA 2 standards.
Okay, and here is a question, a technical question. What percentage of the stored hydrogen energy is used for high pressure storage and liquid hydrogen?
I don't know if can you say that again? I don't know if I understand.
No, I think maybe the question is referred to, you have all the chains to produce hydrogen, or to produce and handle our hydrogen, and what percentage of this part of you spent in the storage and compression?
You mean of the cost of hydrogen?
Yeah, energy percentage. Yeah, energy.
The energy. I don't know.
Do you have a number?
No, I don't really have a number for that right now because I don't think I completely understand the question. But if I will try to clarify that and then supply an answer if we can.
Okay. And about the haulage truck project in South Africa, how much cost, or do you have any estimate costs to adapt the mining truck to the fuel cell system, for example?
No, we don't. Since well, right now that's a proprietary project when it comes to cost. So I cannot divulge the pricing, the costs associated with the system, our system. But as far as converting the truck, that was they are not using our powertrain or our fuel cells, so we are not involved in converting the truck to run on hydrogen. We basically just installed and supplied the compression, storage, and dispensing.
Okay, and in your experience, or what you are expecting, what cost of hydrogen do you expect for 2024 or 25, etc.? What is your projections or tendencies?
Well, it all depends on what production system you're going to use. For instance, right now, the cost of a kilogram of hydrogen, of liquid hydrogen in the United States is somewhere between $5 and $7.50, $8. And the range is, again, primarily dependent on the distance from a liquid facility to where the hydrogen is going to be consumed. In gaseous hydrogen at this day, today, in high pressure systems, is probably somewhere in the $8 to $11 per kilogram range, again, depending on how far you have to transport it. For low pressure, it's anywhere from 15 to 20 kilograms, depending on where it's being produced and how far you're going to transport it. With electrolyzers, that is all dependent on the cost of energy. And for instance, if you have a cost of energy of 7 cents per kilowatt hour, taking into account an all-in price of capital plus utilities, you could you can have a cost per kilogram of hydrogen produced of somewhere between $5 and $7 per kilogram. So it's very comparable to liquid deliveries in the US. So electrolyzers are becoming, if you have a low cost of energy, are becoming more and more comparable to liquid hydrogen deliveries. And as far as 2024 is concerned, all I can say is it's going to be, the cost of hydrogen is going to be much lower than it is today.
Okay, and you show some transport application, and how is today the cost of hydrogen for heavy transport compared to the LNG, which is also being developed now? You are competing different technology, and what
Correct.
can you say about the hydrogen heavy transport, for example?
On the fuel to fuel cost, it's hydrogen is more expensive, the LNG, no question about it. But again, it's that technology, or that cost, is going to be coming down, and we predict that it's going to be cost neutral within in 2023, 2024, because there is so much more capacity being invested. Plug Power alone, we plan on investing in renewable energy in the United States, and by 2024, right now we have, with our United Hydrogen, we have a capacity of producing about 6 tons of liquid hydrogen a day. Our stated objectives and public objectives is to have about a capacity of 40 to 50 tons a day of renewable hydrogen by 2024. So that allows the cost of hydrogen to come down compared to LNG, but right now it is much more expensive.
Okay, we have several questions here, but the time is running. But just two question more. The project discussed in South Africa, does this mining truck run 100% of hydrogen, or is a hybrid solution? It's a hybrid solution, and I can get more information, but I think this project is a well-known project that there's been articles published on it, but it is a hybrid solution. It's not just a hydrogen system. Okay, and the last question is related with your company in Chile. What are Plug Power's next step with this type of technology, and how do you see the Chilean market for project development? Well, we are currently working with 2 partners in Chile.
That is the Engie group and Buso group. They are partners, and we are actively supporting them in projects in Chile and in the rest of Latin America. And we are also working with two other companies that we have not finalized the agreement, the partner agreement, but both these companies are energy companies. And they realize that, as you stated, Chile is going to become a hydrogen market and pushing. So Plug Power is actively working through partners to support the development of the hydrogen economy in Chile, and we are very excited to do that.
Okay, the time is over, but we have to. I would like to thank you, and I switched to Spanish because you speak Spanish, but you know you speak very well. Cambio entonces a español. Yo sé que Fernando además habla también muy bien español. Él cree que no tanto, pero en realidad habla muy bien. Pero prefiere obviamente hablar en inglés para temas técnicos. Así que agradezco mucho su presencia. Me preguntan por interno si es que podemos compartir tu correo para que te contacten las personas.
Sí, claro, sí. Sería mi placer.
Ok, perfecto. Así que muchas gracias nuevamente. Muy interesante esta charla. Yo creo que con esto vamos creando todo un ecosistema de nuevos conocimientos para las distintas compañías. Así que muchas gracias nuevamente. Muchas gracias, Fernando. Y nos vemos en 2 semanas más hablando de estaciones de servicio y otros temas. Así que muchas gracias. Hasta luego.
Muchas gracias a todos. Adiós.